introducing Peter von Kranenburg to you, which you all know already. He has a background both in electrical engineering and in musicology, and his PhD thesis was on content-based retrieval of Dutch folk songs. And he is now a postdoctoral researcher here at the Meertens Institute. And his talk is entitled On Computational Modeling in Ethnomusicological Research Beyond the Tool.
Thank you. Well, I'm quite happy with the talk by Daryl. He kind of paved the way for this more general and methodological questions. I want to say something about modeling in musicology, and there are several reasons for doing that. I'm not having the illusion that I'm telling something new, but given that we are with such a mixed group with different backgrounds, I think it's good to have these methodological questions addressed. And the second reason is not too many, at least not too many music information retrieval researchers are pursuing these methods. So therefore I think it's interesting to go into that. So there's a lot going on in digital humanities, and terms that are all the time. You can hear tools, data, models. Data, of course, is at the center. We all have these digitized data sets, digitized music, digitized newspapers, digitized whatever, and we want to extract knowledge from that. So that's actually the basic idea. We use tools and we build models, and there's also the computer, which actually doesn't exist. But the computer is has not the central part that you might think it has. It is merely just executing orders and nothing more than that. So I will focus on tools, data and models. Maybe you have ever seen this. If you go to the north of the country, in Friesland, in Franeker, there is a 18th century planetary, IJsinga, in the ceiling of his living room. He built this planetary, and if you go upstairs and see what's above the ceiling, then it's like this, all these mechanics going on. And so all this is turning and moving, and reflects the movement of the planets and the moon and the sun in orbit. And well, there's much more. The time the moon is, the phases of the moon are also somewhere, and it's a very rich model. And we could consider this a mechanical model of the solar system. And I want to use that to get these terms, tool and model, a bit more clear. Apparently when IJsinga built this model, he used tools, like hammers or whatever they used in the 18th century. But the key difference is these tools, after he built this model, these tools were put away, and they were only used to build something, and they are not in the final result. While this model, this mechanical model of the solar system, is actually a mechanical model. The very thing itself is you could say, research result. He tried to build a model of the solar system, and well, one could test the model by actually checking if the orbits in his ceiling correspond with the orbits of the planets and the sun, as you can observe. So tools and models are, in this case, both mechanical, but for computational tools and computational models, I would say the same applies. For example, if we have a pile of scores, musical scores, and we want to know something, for example, we have all the compositions of William Byrd, and we want to know how many C sharps did he write, for some reason, I don't know, but maybe we want to know that. Then we could, of course, go over all these compositions and count. But it would be easier to do that with a computer, right? But then we have a problem, because if we scan all these scores, we still cannot search for C-sharps in that. We need, for a computer, it's better to have a text representation of the scores. So it's as it's shown on the right in current representation. And in that you can very simply search for all C-sharps. But to get from the image of the score to a text-based representation, that's a very important step, a crucial step, if you want to do this. But it is not necessary for the result. So it's a tool. But at the same time, the question how to do this, how to get from score to some other representation, it is a research question. But it is not a research question for the musicologists looking for C-sharps, but for some other kind of information scientists who want to solve this problem. So the actually model that is behind this, going from score to a textual representation, is not relevant if you want to look for C-sharps. But it is relevant, it is a research topic, if you are an OMR researcher. So tools and models are determined by their use, rather than being research topic in itself. So that's what stated here. And I will also state that computational research is something else than tool building. It's often in these digital humanities discussions, there's overlaps, but I think it makes sense to make a clear distinction here. So what then about modeling? I will present a way of thinking about computational modeling that is based on McCarthy's book Humanities Computing. In that book he describes the very abstract level ideas and methodology for doing computational research in humanities, and I want to make that a bit more concrete for doing music research. So this schema very much resembles what Daryl told us. There's an algorithm, classification algorithm or clustering algorithm or whatever, that gets input, formalized data, scores, audio, ethnographic data, texts, etc., and delivers output, a classification, similarity measure, a distance value, a clustering of objects, etc. Now, of course, if you want to apply this to a certain research field, for example music, then we need to incorporate knowledge about music into this input, this formalized data, and into the algorithm to a certain extent. And then the algorithm tells us something, we have to interpret that, which is a very crucial step, and there are many problems in that, and I will come back to that. And the interpretation of this output can be used to improve the domain knowledge or the hypotheses we have about the object of study, and can be included in the data and the algorithm, etc. And thus we have a research cycle so that we can continue to build knowledge. So an algorithm expects structured data as input. That means we have to formalize our data. And formalizing data in itself is an act of modeling. Now the case is, which is very lucky if you are a digital humanity researcher, that within computer science, within information science, many abstract data structures and abstract algorithms have been developed that can solve all kinds of problems at an abstract level. And I think that's a crucial point. I collect some examples. For example, a graph. Many of you will be familiar with graphs and all these kinds of data structures. Many others are not, I guess. So I will go a bit into these examples. A graph is simply just a collection of nodes, the circles, and edges that connect these circles. So you can build a network, and the edges can have a direction and a weight. That's all. And it's not, so it's still without meaning, it's abstract. What is a node? What is an edge? Can be anything. So it can be used to model communication networks, for example the internet. Then the nodes are computers, and the edges are the connections between computers. Social networks, then the nodes are people, or Facebook profiles, or whatever about people. And the connections, the edges, are some kind of relations between people. In route planners it is used. Then the nodes are cities or places, and the edges are roads or distances, etc. Models of the brain, molecular structures, relations between tunes. Anything that is a network can be modeled with a graph. And there are many, many algorithms that can extract structure and find structure in graphs. For example, the graph at the bottom shows a minimal spanning tree, which is a subgraph that connects all nodes and has minimal weight along the edges. Still, it's abstract, but in a certain concrete research question, this can be very important. Something that was done in Utrecht a couple of years ago by Alberto Pinto, as an example for music, was to represent a melody as a graph. So now the nodes are pitch classes, and the edges are transitions between nodes. So then you can represent any melody as a graph, and then if you have two melodies, two graphs, compute a kind of similarity measure or similar things. So a tree. A tree is another data structure. It's a kind of graph, but it's hierarchical. And we can use it, for example, for parsing trees in grammar, and also parsing trees in music, of course. Another kind of data structure is a weighted point set. Nothing more than a point, a location in a space, with a weight. Still abstract, it can mean anything. So also in previous research at Utrecht University, it was made concrete by regarding the pitches and the time as the determinants for the position in space, and the duration of a note for the weight of the point. So if you then have two melodies as weighted point sets, you can compute a similarity measure. Another example of data structure is a sequence of symbols. So we have one sequence of symbols, X, consisting of 7 symbols. Another sequence consisting of 6 symbols. Still, symbols can be anything. Can be letters in a word, words in a sentence, notes in a melody, etc. And there exists an algorithm, Daryl already mentioned it, that can find an alignment of 2 sequences of symbols that can be considered the best alignment if you provide a certain score function. So these are 2 possible alignments. There's another alignment, and there are many alignments possible. So this is a search problem, and there's an algorithm that can solve that efficiently. And this is an example with 2 melodies. 2 melodies, and the alignment is in between, as computed by an algorithm if you provide a scoring function for aligning notes. So again, from abstract to concrete. Now if we go back to our model, the interesting point that McCarthy makes in his book Humanities Computing is by the interpretation of the algorithmic output to especially look after failure. Where does the algorithm fail? Because there is an opportunity for knowledge gain. And here is the same cycle in text, with 2 other items added, I would say very important ones. So if you do such a research, the first thing is to understand the humanities problem by knowing the relevant literature, knowing the academic traditions, knowing the specific discussion. So in our case, a lot has been written about music, music theory, music analysis. That can be a starting point or be used to avoid pitfalls in modeling. Then designing meaningful data structures and algorithms, which can be considered a hypothesis of the musical phenomenon we are studying. And then interpretation of the algorithmic output. Where is the failure? The revision of the model, go back, and then we are in the cycle. And in the end, it would be nice, of course, if the results of that could be integrated in our case, in the musicological discourse. Now, how to find appropriate algorithms in data structures? I think that's an act of creativity of the researcher. So you have to somehow make the link to get an idea for a certain musical problem, to use a certain model or a certain data structure. Therefore, it requires knowledge from both domains. And the sentence at the bottom is by Leonard Meyer. I think it's very to the point here. He says, the better the terms and threads of the algorithms, so that's our nodes, edges, symbols in a sequence, the better the terms and threads of the algorithms and data structures are interpretable from a humanistic point of view, the more the results contribute to humanistic knowledge. That's maybe a nice statement to discuss. But there's one big problem, how to evaluate the output of the algorithm. A common approach is to assemble a set of ground truth data, which is considered the correct output, and then compare what the algorithm does with the correct output. However, there's of course a problem here. What is the correct output? In many cases, we will not know. There is discussion, or it is simply unknown. And this is a question that I encountered in some studies from music information retrieval. We ask a musicologist to provide a label or whatever, a segmentation, and then we have our truth, and then we compare our algorithm with it. The musicologist always is anonymous in that case. So there seems to be a separation, a division between worlds. But what happens then is that an algorithm is evaluated concerning its ability to reproduce the ground truth instead of understanding it. So then the question is how to evaluate the results of an algorithm. And so this method of using ground truth and testing the algorithm is of course very appealing because it's simple. You very quickly have results, and if they are better than earlier publication, you can publish these results. If you go into this ground truth problem, so by studying both the ground truth data or the reference data and the algorithmic output, then you're more on, could have the feeling to be more on shaky ground, and it will probably take more time, but I think it would be worth the effort. So I do not think there is a general answer to this, but the key point is to in the evaluation of the algorithmic output, also to reconsider the labeling or the segmentation, and to see what knowledge can be gained there about the musical data. So some perspectives to conclude with. I think computational models can help to understand music in the way I described. It is the creativity of the researcher to properly connect abstract data structures and algorithms with terms and concepts related to music. And computational models of music, I think, need to be related to the musicological discourse. And finally, since computational models are explicitly defined, it is less difficult to work on a collective body of knowledge. Algorithms and data structures are kind of explicit, so you can more easily debate and reflect on it and build a common body of knowledge. Thank you.
Thank you very much. Questions?
Thank you, Peter. So I feel like one area where, as musicologists, we really kind of bear the brunt of some decisions that come out of the data structure research community. Music is a very complicated data structure, and it's really appealing to think of something like a minimum spanning. You'll come up with a graph, find a nice musicological interpretation to the minimum spanning tree. It'd be very, very interesting when you can do something like that. On the other hand, we're doing empirical research, we're dealing with corpora, we're generally not looking at every piece of music that's ever existed, and so on some level we also need to use statistical tools. But usually there aren't very good statistical models for algorithms as complicated as a minimum spanning tree, and if you look at standard statistical models, as an algorithm, as a model, they're so simple that often that musicologically they're not very interesting. And I know that you're not going to solve that conflict in an answer to a question in 30 seconds, but do you see at least potential for kind of reconciling, more complicated traditional algorithms that might be more interesting musicologically, and statistical methodology that's perhaps more appropriate for empirical work, but sometimes is so simple that the results leave you feeling flat?
Maybe it depends on where you take the starting point. So, if you have a specific musical problem, like in our case we are dealing with melodies that are in tune families. So the speakers are in the ceiling, so it might help to microphone a bit. Okay. I was saying it depends on where you depart from. So if you depart from the musical problem, then the choice of model or modeling type, or either a computational model or a statistical evaluation of data, might be motivated by that. So I wonder whether reconciliation at that level is really necessary.
I don't think I need the mic. What is your interpretation of Meyer's comment there? What does he mean by data structures, I forget the exact wording, evaluated from a humanistic point of view? What in your opinion did he mean there?
Well, the terms and threads of algorithms, like if you have well, there are computational models that are so complicated that you cannot anymore understand how decisions or predictions are being made. Then you have output, but you do not know how this output got there. So there's not much.
Did he specifically use the word data structure?
No, I'm sorry.
Or that's your words.
It's I have to correct that. So it is I'm paraphrasing him here. I did not put his name underneath, and now I know why. But yeah, I have the exact citation somewhere if you're interested. But he did not. Indeed, he didn't use those terms. Yeah.
One last question.
Would you suggest that in order to communicate, let's say, engineering approaches with musicological knowledge, that everybody should himself obtain some kind of knowledge from both areas, or how should communication optimally work? I mean, everybody of us in engineering gets more and more into some really complicated stuff, and that gets more and more difficult to communicate with musicologists, and vice versa.
Yeah, that's a very, very important question. There are not many people who combine both backgrounds, but so communication and teamwork is, of course, very important if you want to do this. And the willingness and openness to understand terms and concepts, and there can be very much noise in that communication. So it's really a challenge. But yeah, I guess good teamwork will do it.
Thank you again.